I don't remember missing. Okay.
Well,
So
it's
why do loops commute? So it's loops is a limit. It's a map, right? And but you're mapping into a filter colimit, and the thing you're mapping out of is what? A circle. So you're using the fact that the circle is compact. That's why it
yes,
maps out of it with the filter colimit.
yes.
Not just compact, but really like a finite homotopy type.
Well, in the Hausdorff case, and maybe more generally, a map into the direct limit with the direct limit topology. A map from a compact space into the direct limit is in some finite finite stage of the limit.
Sure. Okay.
Okay, so we do get an omega spectrum starting from an arbitrary spectrum, and the homology groups in the right hand side of the Madsen-Weiss theorem is simply the homology of the zeroth space of the omega spectrum constructed from the spectrum AGN, comma 2, which is a sort of a Thom spectrum, but not exactly. Now, in other words, it's the direct limit of the homology of the loop spaces of and I want to put a 0 here to get rid of to get rid of all components of the loop space which do not contain the unit element. Okay, now does any of this make any sense whatsoever?
So this first equality, you're going from homology of this infinite loop space to the zeroth space. This is kind of by general principles.
Well, I think it's the definition. Correct me if I'm wrong.
I would have said the definition was like smash with the Einberg-MacLane spectrum. That's the definition I know, but
okay.
then the claim would be, I guess, that if the spectrum with which you smash is a suspension spectrum like this, then that just gives the homology of the underlying space that you started with. And I think that's correct. That's like the way to see homology in terms of spectra.
Okay, so Chris says that we need to be more careful, and homology.
No.
Really is the homotopy groups of the smash spectrum, and I agree. Now, I think in this particular case, we still have this equality, but it needs some.
We can take it as a definition if we only know what kind of connective spectra are, and we don't have some more general theory of spectra, then I guess this is fine. You just define homology to be this.
Well, yes. So, by the way, if someone gives a talk about spectra, it would be nice to see a proof of this formula. But the second formula is actually what the proof proves. Well, we'll see it in more detail when we get to this part of the proof. Okay, so now we sort of understand the statement of the theorem, except we have this infinite loop space, which is sort of interesting, but is it really possible to calculate the answer explicitly? And yes, it is. So let me just say that the homology of this thing again rationally well, let me replace homology with cohomology, although it doesn't really make any difference. Let's not do this. Let's just say that we have an isomorphism, but this isomorphism is an isomorphism of vector spaces. Where the kappa 2, kappa 4, and so on are the so-called Mumford-Morita generators. Uh, we will see a topological interpretation. But let's see if well, we have some people here who are probably familiar with the algebra geometric interpretation. So could someone remind us what the kappa classes are? Марк, вы можете нам сказать, что такое капа-классы?
К сожалению, нет.
Так, ну хорошо, я просто забыл. Кто-нибудь помнит, что такое, как определить капа-классы?
Если я правильно помню, какая из греческих букв обозначает какие из них, то это просто тензорные степени канонического класса кривой для тавтологического расслоения.
Может быть, это ню-классы, Денис?
Возможно, то, что я говорю, это другие греческие классы, да.
Вот. Ну, я тоже.
Это может быть пси.
Может быть, пси-классы, точно. Well, it looks like nobody remembers exactly which classes are which. So let's just say that these are the Morita-Mumford generators, and later on, it would be nice to have a talk which translates between the algebra geometric definition and the topological definition, which we will see. Anyway, okay. So the stable answer is just a polynomial algebra. It's very simple, and the unstable cohomology of the moduli space, on the other hand, is quite complicated and basically it is known in some particular cases, but not in general. Okay, now let's see. Let's mention a few variants of the Madsen-Weiss theorem. Well, first of all, there is a simpler variant, which is the Barrett-Predict-Willem theorem. And it says the following. Let's take the direct limit of the symmetric groups. And again, the cohomology of each individual symmetric group is very complicated. But the direct limit has a simple description in terms of in terms of the omega spectrum constructed starting from the sphere spectrum. So the sphere spectrum is a suspension spectrum of the of 2 points. We then pass to the resulting omega spectrum and do the same thing. We take the basically the zeroth component as a space, and then we take the homology of the resulting space. And well, it looks like it's a hard theorem, and it is a hard theorem, but it's easier to prove than the Madsen-Weiss theorem, because basically this is the dimension zero analog of the Madsen-Weiss theorem. Well, there's another similar result, which
I mean, you're saying it's an analog in the sense that I can think of a symmetric group as the mapping class group of a bunch of points.
Yeah, exactly.
Yeah, that's cute. That's cute.
So even the zero-dimensional case leads to meaningful results. Okay, well, instead of symmetric groups, we could also consider the braid groups, and again the cohomology of each individual braid group is quite complicated. And again, we can take the limit, the direct limit, when n goes to infinity. And this time, the answer doesn't involve any infinite loop spaces. It's just the second loop space of the sphere, of the two-sphere. And later on, we will see the proofs of these statements.
So the homology of the pure braid groups is not too bad, right? Because the classifying space is
yes, of the pure, but then
just some.
if it's not necessarily pure, we get lots of torsion, and as far as I know, there is no explicit answer.
But that difference is just coming, like all of the complexity is, well, whatever the pure braid groups are, which we can understand, plus some relation to homology of the symmetric groups, which is complicated, right? Like there should be a spectral sequence relating
yes
homology of braid groups with, well, with what? It's like
well, we have an extension, what is it? The
so I
braid
guess people
group,
call it Leray, not Leray, Hochschild-Serre.
exactly. So we so we have Bn sigma n 1. We have an extension like this. Does everyone agree? So the spectral sequence will be
This F should be P, but otherwise this is fine.
P, okay. So we have the
But secretly, it's also the Leray spectral sequence, right?
yes. Well, it's a particular case of the general relay spectral sequence.
Кстати, как по-русски называется это спектральная последовательность для фибрации?
Ну, по-моему, так и называется, правильно, последовательность Лере.
Лере, ага. Потому что на английском
Зависит от
топологии...
традиции. Сьерра Хохшильда все-таки, если
Мне кажется, Линдера
придерживаться
Хохшильда, на самом деле.
петербургских традиций, по крайней мере.
Не-не, в общем случае, для фибрации.
Для фибрации. Ну,
А.
значит, здесь вопрос вкуса. Значит, те люди, которые фанаты Лере, говорят Лере. Те люди, которые фанаты Сера, говорят Сера.
Ну, понятно.
Вот
Некоторые люди
на
еще говорят
английском?
спектральная последовательность Гротендика.
Нет,
на английском...
Гриша, все-таки Гротензик это у нас два функтора. Там,
Ну, так это же частный случай.
Ну, понятно, что частный случай, но, значит, вот, но все-таки, вот если никаких функторов нету, то это, значит, или Ре, или Сера. Ну, точнее, если у нас там функторы есть, но они вот такие. But there's a general spectral sequence which corresponds to an arbitrary map, not necessarily a vibration. This one is the Leray spectral sequence, as far as I'm aware. For vibrations, there's Leray,
Не важно, только интересно.
there's Leray, Ser, or any combination of these. Anyway, so there's a spectral sequence, and as one can see, it contains the cohomology of the symmetric groups with some coefficients, and basically it's discouraging. The cohomology of symmetric groups is quite complicated. Okay, so are there any remarks, comments, criticism, protests, and so on? Okay, so before I don't think we should start the proof of the Madsen wise, but let's go through a few topics for talks.
So I think it's not a bad idea based on our experience last year with the string topology seminar. It's not a bad idea to review some things about group homology, in particular how to actually compute some interesting examples. And this might even be enough to explain, well, one can probably explain the idea of the proof of the Barrett Pretty-Quillen theorem. So there are these notes which I can forward. It's a course on homological and representation stability, which starts with some review of group homology and classifying spaces and some techniques for computing. And then I think it does give a proof of this theorem for symmetric groups. And then yeah, what Alexey is writing next is relevant to the surface case.
Well, that's
I'm sure we really want to listen to the proof of Il's theorem, because as far as I know, there's no good proof of this theorem.
In Hatcher's notes, I thought, so Hatcher has a nice set of notes on this Madsen-Weiss theorem, and he gives some proofs of a lot of what goes into it, I think including the Earl-Eels theorem.
Yes.
And the one thing he doesn't prove is Haar stability. So this seems to remain a hard theorem. Now,
so the Earl-Eels theorem says that the connected component of the unit element of the diffeomorphism group of a surface is contractible, except in some cases, namely the sphere, the projective plane, the torus, and the Klein bottle. Basically, there are some exceptions, but otherwise the connected component is contractible. And well, regardless whether or not one likes the proof, this theorem is necessary for the proof of the Madsen-Weiss theorem. So it's not always a question of taste. Well, another thing is we will need to use the classifying spaces for several monoids, topological monoids. And the group completion theorem basically says that even if the pi node of a monoid is not a group, there is still a way to describe the homology of a closely related monoid in terms of some loop space.
okay, so I put 2 references in the chat with links. I think Hatcher also gives some proofs of relevant facts about group completion.
Well, yes, basically all of these topics are in Hatcher's notes, and I think they're quite the notes are quite readable. So one needn't be afraid of any of these topics. Okay, well, this is basically what I can think of at the moment, but there's certainly more. There's certainly more, and we'll later on we'll have more topics and so on. But to begin with, I think these four will do. So if you want to give a talk on any of these, please let Chris or myself know.
Maybe right now we can try to get a volunteer for the talk next week on group homology and classifying spaces. So take a look at the notes that I posted in the chat. There's a nice introduction there, which is kind of tailored to the kinds of things you need for homological and representation stability.
Okay. Are there any volunteers? And by the way, you don't have to know what group homology is in order to give this talk. I would say if you want to learn it, then you should volunteer. If you don't know it but want to learn it, you should volunteer. Кто хочет выучить, что такое гомология групп?
Если знаете больше, я могу попробовать.
Ну хорошо. Да, well, I think Vladimir is probably a good candidate. So, Vladimir, do you understand which set of notes Chris is talking about?
Yes.
It's probably yes, probably the first one. Okay. So. Please try to read the notes, and if there is anything inside those notes which you don't understand, please let Chris and myself know. The idea is well, it's well.
So Alexey's beard is even grayer than mine, but I can be found on Telegram. So that's
okay.
actually a good way to ask me a question. You're more likely to get a fast answer that way than by email.
Так, значит, Володя, еще раз, если там что-то непонятно, то, значит, мне очень спросите Криса или меня.
Хорошо.
Ну, я не участвую в Телеграме, но там, но на e-mail отвечаю. Да, и по поводу записи. Значит, давайте я спрошу Казаряна и Ланду, кто организует вот всю вот эту красоту, которая там происходит. Значит, тогда я просто предлагаю спросить этого человека, и сразу все станет понятно. Можно еще спросить Колезина. Колезин, в принципе, там делает то же самое, только в другой комнате. Okay, well, the time is running out again, as it always does. Is there anything else we need to talk about?
Well, I had a question about this result on equivalence with the ring of polynomials, but I guess maybe now it's not the time to ask. I don't know.
Well, let's. Well, we'll talk about this result in detail.
Okay.
We will see a topological interpretation of these classes, and there is a geometric one, and of course one would like to understand how to pass from one to the other and back again, and well, it's another potential topic for a talk. How to relate the topological picture to the geometric picture.
Yeah, no, I guess I was curious, is the topological picture related to complex Bardisms, because it looks suspiciously like the ring of...
Well, offhand, I don't know. Chris, what do you think?
The question is whether it's interpretable as some cobordism ring.
Yeah, so is there like a formal group law, and can this be promoted to an isomorphism of rings and stuff like that?
I don't know. I thought the story about group laws was about complex oriented spectra.
Yeah,
so
but
I don't.
I mean, that's just the same ring, basically. So
Well, like, I don't know. I've never seen this discussed. I mean, maybe it's a question that can be made sense.
Я бы сказал, что
Made
много
sense of.
колец изоморфны целым числам, но не все из них как бы имеют одинаковое происхождение. Ну, кольцо Лазара не сильно отличается от кольца целых чисел.
В общем,
Не везде, где оно встречается, оно
в общем, ответ, что
является гомологиями чего-то.
значит, непонятно. Значит, непонятно. But we will get kicked out of the room in a few seconds. So, is there anything else we need to discuss? Well, it looks like the answer is no. So, see you all next week, hopefully in room 208, and in